Okay, today we're going to start talking about the Frobenius method. The posted video does an excellent job at providing context, but I think they launch right into it with a problem with a singularity, and we'll talk about those a little bit more later on in my second example video. For this first one, I just wanted to demonstrate the method, once again under a situation where we are comfortable with the equation we're dealing with and with the solution that it has, so that we can anticipate it and learn the method without necessarily having to be confused by the context. So we're going to go back to our old friend, the Euler-Cauchy equation. As you recall, those look like this: x squared y double prime minus 4x y prime plus 6y equals 0. It basically was a linear second order homogeneous differential equation with variable coefficients, but it always had a power of x associated with the order of the derivative. So it was x squared with the y double prime, x with the y prime, and a linear term with the non-derivative y. We won't necessarily always end up with something that matches this pattern, but equations like this with more complex functions sitting in the positions of the coefficients, these are the equations that are generally solved by the Frobenius method. The purpose for the Frobenius method is really when these have singularities in them, the coefficients of the y prime and the y term. Basically, they end up with polynomials in the denominator that have 0 points, so that these individual coefficients would blow up at a certain point: x equals 0, x equals 1, x equals -2. And that's what the Frobenius method is really ideal for. It's ideal for solving equations at a point where the infinite series would not only not converge, but couldn't be used because it has no definition at that singularity. So let's use this one as an example for how Frobenius works, and then we'll apply it to some more sophisticated problems looking at the different cases tomorrow. For today, all I want you to focus on is being able to determine what's called the indicial equation of these differential equations that you'll be applying the Frobenius method to. Okay, the first thing I wanted to do was review how we went about solving this to begin with. So our method of solving an Euler-Cauchy was to take the guess that the solution looked like the form x to the m. And then the consecutive derivatives of this would be y prime, which is mx to the m minus 1, and y double prime equals m minus 1, x to the m minus 2. It was convenient to use these solutions because they helped us with these variable coefficients that contained x's in them. As a matter of fact, if it had all the terms in an Euler-Cauchy, it does something nice upon substitution. So when I substitute in for y prime y and y double prime, what we end up with is m times m minus 1 times x to the m, because the minus 2 is taken care of by the x squared, minus 4 m x to the m, because the minus 1 is taken care of by the x, plus 6 x to the m. And then I'm going to do something here that we didn't really do a lot of before, but let's factor this out and look at it as m times m minus 1 minus 4m plus 6, and then it's that whole quantity times x to the m. And if that's equal to 0, I know x to the m won't be 0 because there's almost no exponent I can use that will make that 0, as long as x itself isn't 0. And that means this has to be 0, and that's how we got our characteristic equation for the Euler-Cauchys. I'm going to show you a shortcut later on in my second video that'll tell you how to get to this quicker, including these equations that we're going to be doing with the Frobenius method. Okay, so that means this right here has to be equal to 0. So I can multiply it out, turn it into hopefully a factorable quadratic. I got m squared. It'll be minus m minus 4m, so that's minus 5m plus 6 equals 0. This factors easily into m minus 2 times m minus 3 equals 0, which gives me roots of m equals 2 or 3. We can then take those and apply them to our original solution guess, which is this will give me two linearly independent solutions, each of which has an arbitrary coefficient, which I would resolve with boundary conditions, but the solution would be y equals c1x squared plus c2x cubed. Okay, I'm going to move that back to the top just so we can remind ourselves of what that solution was. c1x squared plus c2x cubed. And in particular, I wanted to go through this method, particularly because the Frobenius method feels very, very similar to it. We'll just be using infinite series to substitute in for that x to the m. The trick with the Frobenius method is we need extra powers of x in order to take care of our infinite series around the singularity. So instead of our guess being the standard power series, summation n equals 0 to infinity of a n x to the n, we're just going to add on a power of r. So in essence, we're multiplying the summation by x to the r. And that sort of substitutes for our x to the m that we used as a solution to this before. What this allows me to do is to use a power series solution on this, even though if we put it in standard form, there'd be an x squared in the denominator here, and an x in the denominator here. So of course that means this series would not have a series definition at a center x minus 0. And of course that's what we're trying here, our x minus x naught to a power. So that's what the x to the r is going to do, is it's going to help fix that. Okay, let's look at the consecutive derivatives. Y prime is equal to the summation n equals 0 to infinity of n plus r a n x to the n plus r minus 1, and then y double prime is going to be equal to the summation n equals 0 to infinity of n plus r times n plus r minus 1 times a n x to the n plus r minus 2. And then I'll simply substitute these in, and I'm going to keep them as the series definitions. I'm not going to expand these. So it'll be x squared times this, and you can see that'll resolve the minus 2 at the end. So the first term will just be n plus r times n plus r minus 1 a n x to the n plus r. And of course this has a summation in front, n equals 0 to infinity. And moving along, minus summation n equals 0 to infinity of 4n plus r a n x to the n plus r. And then finally 6 times that. So plus summation n equals 0 to infinity of 6 a n x to the n plus r. And that all equals 0. So far this looks pretty similar to the method we used before. It can get a little difficult with the exponents since we've added on the r, and then sometimes with consecutive derivatives and multiplication we won't always have perfect powers lining up, but sometimes they do, and that makes the problem a whole lot easier. Okay, since everything's in terms of the same power of x, and everything begins with the same index, we can go ahead and factor. So this will be a single summation, n equals 0 to infinity of n plus r times n plus r minus 1 minus 4n plus r plus 6, and then all of that is times a n x to the n plus r. So we end up in the same position we were in with the Euler-Cauchy and the characteristic equation, which is we were in this position where I was pretty sure that x to the n plus r is never going to be 0. I don't want all the coefficients to be 0, because if they are, then the series solution is trivial. It's just 0. So I need to preserve at least some of these coefficients, which means whatever's going on in here, this is where the zeros are going to have to come from. So what I want to do is just guess, or actually select, one of the coefficients. I'm going to select a naught. I would like a naught to not be 0. So I'm going to look at what the first term's coefficient would be here, so that times a naught And again, if we're at 0, then it's just x to the r. So I just want to build the first term. When n equals 0, what does this thing turn out to be? So let's just rewrite it. So at n equals 0, this is what we get. N plus r is just r. N plus r minus 1 is just r minus 1. Minus 4n plus r is just 4r plus 6. We've got this guy right here times a naught times x to the r. And because that's the only term that's going to produce an x to the r is n equals 0. N equals 1 is going to make r plus 1 and then all the way up. I know that this whole coefficient here has to make the equation true, so that either a naught has to be 0 or what's in here has to be 0. And I'm going to choose a naught deliberately to be non-zero. That means this has to be 0. And this guy right here has a special name. This is called the indicial equation. And what it's going to do, in this case it's quadratic in r, it's going to give me the values for r that allow this series to actually have solutions. If the values of r here don't produce 0, then the series itself has no solutions, because if this is not r, then a naught has to be r. And if a naught has to be r, maybe a1, a2, a3, maybe they're all 0. So I'm deliberately choosing a naught not to be 0, which means it limits the values that r can take on. Let's look at what they are in this case. This is going to look familiar to you. R squared minus r minus 4r is r squared minus 5r plus 6 equals 0. Notice that's exactly the same equation we got when we were solving this as an Euler-Cauchy. So it has the same roots. R is equal to 2 or 3. The difference here is that r doesn't actually represent the solutions. It just represents how we're modifying the series. So what we need to do is deliberately look at these individually. So I'm going to choose r equals 2 first. When r equals 2, that means this series doesn't look like this anymore. We can actually fill in the fact that r is equal to 2. So let's fill that in. So now the series reads summation n equals 0 to infinity. And again, it's going to be n plus 2 times n plus 2 minus 1, which is n plus 1, minus 4 n plus 2, plus 6. And again, all that is going to be a n x to the n plus 2. Again, this is only one possibility. R could also be 3, but I'm just looking at the r equals 2 possibility first. Once again, this series still has to add up to 0, so it's still under the same constraint it was before. And again, I had indicated over here I didn't want a naught to be 0, so let's check out what a naught is in this particular instance. That is, let's go ahead and evaluate the first term of this series, knowing that a naught won't be 0, and of course x squared won't be 0. What does this have to be then? Well, again, if a naught's not 0 and x squared isn't 0, this has to be 0. So let's check on the constraints on this. This is not the indicial equation. These are just the constraints under r equals 2. So let's check out what they are. So I need to expand this out. This is n squared plus 3n plus 2 minus 4n minus 8 plus 6 equals 0, because again, that's the constraint I'm putting on it. A naught's not equal to 0, and x squared's not equal to 0, so this has to be 0. Well, that's going to be n squared plus 3n minus 4n is minus n, and then plus 2 plus 6 minus 8 is 0. So there it is. N is going to have to be 0 or 1. That means this index is no longer an infinite series. N can only be 0 or 1 because at every other value, when n is equal to 2, this can't be 0. And of course, when n equals 2, this is x to the 4th. It can't be 0 either. So that means a2, a3, a4, a5, a6, all of the a's beyond a0 and a1 have to be 0, because it's the only way to make this equation true. N will only make this 0 at 0 and 1. X will never be 0, and so an for all other n's besides 0 and 1 has to be 0. It's the only way to make this equation true. So that means I can write down our solution. It's the original guess with only the first two indices applied, and r is equal to 2. So let's see what it makes. y is equal to the summation n equals 0 to infinity. Well, no, only the 0 to 1. So it's y equals, the first term is going to be a0 x to the n plus r, but n is 0, so that's x squared. And the second term is going to be a1 x to the n plus r, and that's 1 plus 2, which is 3. And there it is. That's the solution to the series. It's the same solution we got before. You might wonder why we didn't have to check R3. Well, R3 will end up producing the exact same solution here. It'll just move the indexes around, and it'll make the n values have to be two different values that compensate for the higher value for R. Go ahead and try it yourself and see that when R is equal to 3, we're going to still get the same solution. So this is how an infinite series modified with n plus r can be used to solve problems even at their singularity points, which is pretty nifty. Now, unfortunately, this is only one of several different cases that we'll look at. So for tonight's homework, what I want you to focus on is taking the equation, no matter what it is. They won't all be in the form of an Euler-Cauchy, but I want you to take those equations and I want you to turn them into their indicial equation so that you can then identify which one of the three cases this represents. More about that in the next video.